I could just stop here with this piece of advice from Alexandre Dumas, but actually, I think today's talk is going to be about, maybe we don't have to wait that long, and maybe we don't have to rely too much on hope to do MCMC in a principled way. So the goal of this topic is to figure out what are, I would say, 3 essential control parameters in most MCMC algorithms, which is figuring out the number of chains, figuring out the number of what's called warm-up iterations, and figuring out the number of sampling iterations. And in particular, we're really going to try and set up a framework so that we can reason about this question. And also, I want to kind of go over how modern computation and the changing landscape of hardware is changing our answer to these questions. I should mention that this is based on a chapter I wrote with my colleague Andrew Gelman that's going to appear in a handbook of MCMC. And there's already a preprint of that chapter. So to ground our discussion, I'm going to say that the main goal when we're doing MCMC is to compute these Monte Carlo estimator to estimate expectation values with respect to certain measures P. Right, so if I'm doing a Bayesian analysis, P is a posterior distribution, but it can be a number of other quantities. And my Monte Carlo estimator is simply going to be a sample mean, where my draws are going to come from some distribution P hat, which hopefully is a good approximation of my target distribution P. And to understand the quality of that estimator, I have to analyze what is its error, and it'll be very convenient to decompose the expected squared error into a squared bias and a variance term. Now, the bias comes from the fact that in many applications, I'm not actually sampling from the target distribution P, but from some approximation. And the variance is mostly going to be driven by the fact that my sample size is finite, and also on a related note, the fact that my draws from P hat are going to be autocorrelated. Right? So those are the 2 sources of errors that I need to control in order to get useful Monte Carlo estimators. So just to say a little bit more on variance, if somehow I was able to draw exactly from my target distribution P, and that these draws were independent, so IID, independent and identically distributed, then actually the variance of my Monte Carlo estimator would simply be the variance of the quantity I'm interested in divided by the number of samples. Now, in practice, we like to reason about a quantity called the effective sample size, which tries to account for the fact that samples can be autocorrelated. And the way I like to define effective sample size is just a ratio of variances, right? The variance of my target divided by the variance of my Monte Carlo estimator. And if you were to plug in this variance up there for the IID case, you would see that your effective sample size is equal to your sample size, right? But in practice, my samples are positively autocorrelated, and this is going to induce a loss in information. And what that means is my effective sample size is going to be smaller than my sample size, right? In other words, if I want to achieve a Monte Carlo estimator that has the precision of drawing n independent samples, I actually need to generate more than n samples with my estimator. So the first tip that I'll say is, when you're trying to think about what variance you need, don't think simply about sample size, think about effective sample size. And use estimators of the effective sample size. There are actually some pretty good ones out there. Okay, so now I want to think about what is the error that I can tolerate with my Monte Carlo estimator. And just to simplify the discussion, I'm going to say, suppose there's no bias, right? I want to ask the question, what is an effective sample size that I should aim for? Right, and that's going to inform how much computation I should throw at my MCMC. So just in the audience, how many people use Markov chain Monte Carlo or have used Markov chain Monte Carlo for their problems? Okay, wow, so that's actually more than half, which I guess is why you're showing up at 9:45 in the morning. Okay, so among those people, what is an effective sample size that you typically use for your problems? Anyone want to volunteer a number? Who uses 10? 100? 1,000? 10,000? Okay, 100,000? Okay, good. So we have a range between 100 and 10,000, right? So let's think a little bit about this. I'm going to look at one application, one very concrete application, just to motivate how we might reason about this. And this is in epidemiology. We actually have some data from an influenza outbreak, and we're going to fit a model, conduct a Bayesian analysis, and characterize our posterior distribution using MCMC. And what I'm going to say is my goal is to estimate what is the recovery time of a patient, right? Maybe I'm a nurse. I'm trying to allocate hospital resources. Or maybe I'm sick. I'm trying to figure out if I can go on my weekend trip. And what we're going to do for this is we're going to report the posterior mean, but also a posterior interval, right? And I'm going to do this with two different numbers of draws. One of them is I'm going to use 4,000 draws, and then I'm going to run the experiment 5 times just to see what kind of results I get. And this is the default number of draws you would get with a statistical software like Stan, right? And then, just to be cheeky, I'm going to see what happens if I divide my computational cost by 100 and I only generate 40 draws. And I should say that, for this problem, 40 draws corresponds to an effective sample size of about 20. So I lose some information because of the autocorrelation, but it's not that bad. And the first things I'll notice is that if I look at the precision with which I'm estimating the mean, with 4,000 draws, I'm able to get 2 significant digits, right? That's actually not going to be the case if I look at the posterior interval, right? Actually, those extreme quantiles are more difficult to estimate. So if I want that second significant digit, I would have to push for more samples. Now, by contrast, if I look at 40 draws, well, you can kind of see that you're not able to get the second significant digit. You might not even get the first one. And you also have much more variation if you look at the posterior intervals. So you might think, OK, maybe that's a good case for running 4,000 draws instead of 40 draws. Now, my question is, if you're trying to figure out how long you're going to be sick, do you care about the second significant digit in terms of days? No, not really. You don't need that much precision. And I would say the same about the posterior interval. I would say those 40 draws give you just as much scientific insight as the 4,000 draws do. And in fact, I think there are a lot of applications where we can get away with less precision than what is prescribed by default statistical software. The other things that I will say is that this second significant digit, another reason why we really don't care about it, is because it's completely dwarfed by the width of our posterior interval. So if I just think about, I'm doing inference, I'm trying to learn a quantity, in a way I have 2 sources of uncertainty. One is my posterior uncertainty, and the other one is my computation uncertainty or Monte Carlo uncertainty. The Monte Carlo uncertainty is very, very quickly going to be dwarfed by the posterior uncertainty. So you can throw more and more and more computation. You're not really going to reduce your uncertainties that much. At some point, you need to worry about the posterior uncertainty. And if you want to do a better job there, you can either collect more data or improve your model. Right? That's going to matter more than using more computation on Monte Carlo estimators. So here's my tip for practitioners of MCMC. Try, once you've run your Markov chain, have the number of draws and see what happens. Do your scientific conclusions change? Have you been too conservative? Or maybe you're not being enough conservative, right? But that's something worth playing around. Let me look at another application where we apply Monte Carlo estimators, and that's in variational inference. And so here, what we're going to do is we're going to still estimate some target distribution P with some approximation Q, right? So we're going to look at this family of well-behaved tractable distributions, and within this family of tractable distribution, we're going to try and find the best approximation to P, where best is going to be defined by some divergence, right? So my objective function is going to be some measure of discrepancy between Q and P over measurable sets of Q. Right? And the point here is that this ends up being an integral or an expectation value. And so when I estimate my objective function, I'm going to do that via Monte Carlo method to then try and solve an optimization problem. Now, this is a case where actually I can draw exact samples from Q, right? So I can draw IID samples. And so now my question is, how precise should these Monte Carlo estimators be, right? So anyone here does variational inference? Could you? Okay, so a bit less than MCMC practitioners. So when you're doing stochastic optimization, right? What is a sample size that you aim for constructing your Monte Carlo estimators? Who uses 1? Okay, yeah, 1. Some people use 1. 10? 100?
Depends on the hardware.
Depends on the hardware. Yeah, that's a very good point. We're gonna dive into this, right? So let me show you one application, and what I'm going to argue is that it really depends on the variational inference algorithm that you're using. So this is actually applying this to a variational autoencoder problem. And we're looking at different VI algorithms. ADVI is kind of a standard benchmark. We have the Gaussian score matching, and then this BAM. BAM means batch and match. And I'm just going to look at the curve for BAM, which is this white curve here. And what I'm seeing is that when my number of draws is equal to 10, I'm really doing a very poor job solving the optimization problem. If I increase to 100, I have a dramatic improvement. And then if I keep increasing to 300, then my algorithm almost converges instantly. It takes 5, 10 iterations. So this is an example of a variational inference algorithm that really, really benefits from increasing the precision of a Monte Carlo estimator. You can kind of see that pattern for the other VI algorithms, but it's not as strong. At some point, you start plateauing, right? So in this problem, if I were to think about what is a useful precision for my Monte Carlo estimator, I would look at the downstream task of doing stochastic optimization, and I would let that inform. But the hard thing is, depending on the algorithm you're using, depending on the objective function, it can be very difficult to figure out what is a useful number of samples. Now, one point that Bob evoked is that the nice thing is that these samples, we can actually compute them in parallel. So if you're using a GPU, the cost of increasing the number of samples in terms of compute time is really small. If you're running things on your laptop or on CPUs, you incur a larger cost. All right, so here's my tip. When doing VI, try increasing the number of samples for the Monte Carlo and see what happens. I think people tend to underestimate the benefits of doing more stable stochastic optimization. Okay, so this is kind of setting the framework, and we've spoken about variance, but you can kind of extend that to think about what is the error you should tolerate with Monte Carlo estimator. And now I want to talk about bias in MCMC. And I think that there's this notion that goes around that MCMC is unbiased. I kind of want to dispel that a little bit, or at least refine that statement a bit. So the way I like to think about MCMC is that it's a stochastic process which is going to evolve from some initial distribution P0, and that's usually going to be some well-behaved distribution that I can draw samples from, to a target distribution P, right? And asymptotically, we get to P. In practice, we usually get to something that's close enough to P. And so what we're going to do is we're going to have a warm-up phase where we're evolving from P0 to P hat. And these initial samples are going to be strongly biased by my initialization. So we're not going to include them when we construct Monte Carlo estimator. So that's known as the burn-in and warm-up phase, and we'll discard them. But then once we get close enough to P, we're going to say, you know what? I also need to kill off variance, so I need to accumulate samples. I'm going to keep those, and that's going to be the sampling phase. So I'll give you a very concrete example, which is a Langevin diffusion. So you can think of this as a continuous approximation of MCMC, which is a discrete stochastic optimization. And here, what I'm doing is I'm evolving from an initial Gaussian P naught with mean mu naught to a target Gaussian with mean mu. So I follow the stochastic differential equation. And the nice thing is that I can exactly write what is going to be the distribution of a sample at time t. And you can kind of see that it's an interpolation between my initial distribution and my target distribution. And in fact, you kind of move exponentially fast from your initial distribution to your target distribution. So if I were to think about the bias here would decrease. So my initial bias would be at be mu naught. I'd have a mean of mu naught instead of mu. And then I would decrease exponentially towards my target distribution. Right? So there's kind of the sense that, actually, at least for a handful of problems, the bias decreases very quickly. Okay, so what can I do to check the bias? So if I have, so the first thing that I'll say is that if I have a single chain, you know, under geometric ergodicity, so for actually an interesting range of problems, my bias decreases exponentially, but my variance at best decreases linearly. So there was kind of the sense that, you know, by the time your variance is acceptable, you know, your bias will probably be negligible. And I think that's why a lot of the statistics literature has mostly focused on variance and asymptotic variance. We're going to see that in the age of modern computation, this has to change. One thing that people have done is they've used this so-called R-hat diagnostic. And the driving idea of R-hat is to say, well, where does our bias come from? It comes from the initial point P naught, right? If I initialize that P, I won't have any bias. So what we're going to do is we're going to check the influence of the initialization. And the way you do that is you start a lot of chains at different points, and then you compare the outcome of these chains. And if the chains overcome their bias and really forgot their starting point, then the distinct initialization should not change the outcome of the different Monte Carlo estimators generated by each chain, right? That's the basic idea behind R-hat. There are some more sophisticated strategies to control the bias, such as sequential Monte Carlo or unbiased MCMC via coupling. These methods are theoretically very compelling, but they can be very difficult to implement, right? So they're not as general purpose as the R-hat, which comes with less theoretical guarantees, but is very straightforward to implement. Okay, so here's an example of an MCMC workflow, and that's based on the defaults in Stan. So what is the number of chains? Well, 4 to 8 with very distinct initialization. Where does that number come from? It comes from the number of cores you have available on your CPUs. Number of warm-up iterations, 1,000. Number of sampling iterations, 1,000. Okay? So my one reservation is that since the primary role of the warm-up is to decay the bias, and the bias, when you have a single chain or a few chain, usually decreases much faster than the variance, to me, it feels like these numbers shouldn't be the same. Right? I think the warm-up should actually be shorter. Now, to be fair, during the warm-up, Stan does a bunch of things to decrease the variance, so maybe that explains that balance. But the good news is that even though we have these defaults, we're not going to stick to them. We're actually going to check that they work well, right? So we check for convergence with this R-hat statistic. We check for some measure of the effective sample size. And the rule of thumb is you're going to try and aim for an ESS that's slightly around 100. And that's not because this is how precise your Monte Carlo estimator should be for all problems. Rather, that's because if the ESS is less than 100, then our diagnostics are not very precise. Okay, my tip is think of these as starting points and be willing to depart from them and calibrate this to your problem. All right, so now I want to talk about MCMC on modern hardware and how, you know, not only this changes our perspective, but maybe it gives us some more satisfactory answers to the question of, you know, how many iterations should we throw at MCMC? And the first observation is that on GPU, you can now run hundreds, maybe even thousands of chains in parallel using some awesome statistical software. There are some engineering constraints to make MCMC GPU friendly, but there are algorithms out there. For example, the Cheese HMC by Matt Hoffman and colleagues, which are GPU friendly. And so now, if my goal is to achieve a target precision in as short a time as possible, what I'm going to do is I'm going to run a lot of chains in parallel. And now my sampling phase can be arbitrarily short because I'm averaging out the variance across the chains, right? I encourage people to very seriously consider having a sampling phase with only one iteration. That's the thing that minimizes compute time. On the other hand, I'm not able to average out the bias. But then again, remember that for a lot of problems, the bias decreases exponentially while the variance decreases linearly. So that's what I mean by you can get an exponential speed up if you're using modern parallelism. So now, what is the number of chains? Well, the number of chains determines what variance I want to have. And you can think that if I warm up each chain properly, I'm going to have one effectively independent sample per chain. So really, I should aim for one per desired ESS. Number of sampling iterations, 1. That leaves us with the question of what the warm-up should be. And now that question is important because it dominates our computation. The problem is, so initially people were thinking, well, why don't we just compute R hat, right, as we did before? That's our convergence diagnostic. And the problem is you can't compare chains that have length 1 to check the influence of the initialization. So that suggests a fix. So this is a nesting strategy that leads to something called the nested R hat, but actually you could nest any number of convergence diagnostics. And the idea is that what I'm going to do is I'm going to, instead of comparing individual chains, I'm going to compare groups of very short chains, right? And here I can make a more meaningful comparison. But because I want to track the influence of the initial point, I'm going to constrain all the chains in this group to start at the same point, right? And then I do my comparison, right? And this is going to lead to the nested R hat. And if you want some, more theoretical motivation of what this does, what I'll say is that it gives you a consistent estimator of something called the non-stationary variance, right? So this is the variance of a conditional expectation value. In particular, F bar, that's my Monte Carlo estimator, conditional on its starting point. So I look at the expectation of my estimator conditional on where it started. And we have this idea that, hopefully my Monte Carlo estimator forgets where it started. My Markov chain has amnesia. That's what we want. And if it really does have amnesia, then that second variance here, which is really comes from the fact that the initial point is varying, right? The expectation value is not going to depend on Z0, and that variance is going to go to 0. So that, to me, is a very compelling measure of how well we forget our initialization. And this is something you can't do if you're running a single chain or a few chains. You really need to be running a lot of chains to get a good estimator of this quantity. So what value should we aim for? What non-stationary variance should we tolerate? So this is a bit of a heuristic, but the point is, it should depend on your effective sample size, and essentially what variance are you willing to tolerate, right? Here I've put a 5, but you can put any number of quantity. But what I'm saying is the bias you're willing to tolerate, the non-stationary variance you're willing to tolerate, should depend on the variance itself that you're willing to tolerate, right? There's no reason to tolerate, to be much stricter about the bias you tolerate than the variance you tolerate. I mean, you should be stricter, but proportionally stricter. So kind of like looking at, my error decomposition, so going back a little bit at the beginning of my Monte Carlo estimator, right? The way I'm going to decompose it is I have a squared bias plus a variance, and then I can take my variance and further decompose it into 2 terms. This is the non-stationary variance that I introduced at the beginning, and then this is going to be the persistent variance, which you're actually going to measure with effective sample size, or you can just think about, okay, that's lower bounded by the number of chains that I have. And the key here is that these 2 quantities decay during the warm-up phase, whereas this quantity is going to be handled by either the length of the chain during the sampling phase or the number of chains that I have. And one interesting property, so if I just go back to this Langevin diffusion example, is I can show that actually this non-stationary variance decays at the same exponential rate as the squared bias. So I'm not able to directly track the bias, but I'm able to track a proxy clock that has a comparable decay rate as the squared bias. So this is just an example of nested R hat in action over a range of problems. These are not cherry-picked problems. These are Bayesian problems that we actually care about solving. And what we're looking at is this nested R hat statistic. We're hoping that it's close to 1. The point is there's some threshold where once you achieve that threshold, the squared error that you have for your samples is comparable to what you would expect if you were able to take draws from the stationary distribution. Right? So that's some empirical indication that this diagnostic is useful. And by the way, I should say that all of this is conducted with using approximately 2,000 chains, and the sampling iteration has length 1. You can do inference that way.
Sorry, what do the points represent in this plot?
Yes, so what the points represent is, what I've done in the experiment is I've run a chain, and then I interrupt it after 10 iteration. And then for each dimension, I compare a squared error scaled by the true variance. And I also compute a corresponding nested error hat. And that's what appears on this plot. Okay, I'm almost done. So let me just give some outlook, and then we'll have time for questions. So again, we have this fundamental tuning problem when we're doing MCMC. We need to figure out the number of chains, warm-up, and sampling iterations. We have some trial and error heuristics when we're running a few chains. I think we have a more fundamental, a more principled way to do this when we're running a lot of chains. And I think this is a real turning point in MCMC, where the focus is going to shift from asymptotic variance to non-stationary bias. And that's going to have a lot of impact on how people develop and design algorithms, implement diagnostics, and do theory on MCMC. My goal is, I want an MCMC algorithm that takes as input none of those 3 tuning parameters, but takes as input the desired precision for the Monte Carlo estimator, and then adaptively figures out what is the warm-up length, what should the sampling phase. This is what I want. This is what truly black box MCMC would look like. With that, I want to acknowledge some of my colleagues, and we have some time for questions. Yes.
Sorry, just a reminder to please use your seat mics when you ask questions.
Can you hear me?
Yes.
Okay, great. Thank you for the very nice talk. So can you go back to the super chain slide? So where do you split? So within a super chain, you start at the initial point, and is there any heuristic, how you construct this?
Yeah, that's a wonderful question. So thank you very much. So let's say I have a budget of 1,000 chains, and now I need to figure out what kind of partition I'm going to do. Right? And I was trying to, so the way I approach this is, okay, well, I'm computing a statistic, right? A nested error hat, or even some estimator of the non-stationary variance. So why don't I try to control the error of that statistic, right? What is the partition that would minimize the variance? It turns out that depending on where you are in the sampling phase, the optimal choice varies. So early on, when I just start my Markov chain, it pays to have a lot of distinct initializations. And then once I get close to the stationary distribution, the optimal choice is to only have 2 distinct initializations, because you want to, for reasons that maybe we can discuss offline. Right? So there's no optimal choice, and the choice kind of varies. So that's a bit unfortunate. What we ended up doing is, in our numerical experiments, is trying a lot of different choices. And we found that the extreme choices, which is to either have a ton of initializations in small groups or 2 initializations in very big groups, ultimately, in this plot, lead to very unreliable diagnostics. However, anything that's between these extremes, there's a wide range of choices that you can take, and they all work well. So it's not a fine-tuning problem, but it looks like you have to stay away from those extreme choices, which are going to be optimal at the very beginning and at the very end. Thank you. I think we have time for one more question. One more. Who will do the honors? Yes, the gentleman with the red.
I don't want to take somebody else's question, since I can talk to you anytime. But one way you can deal with answering the thing on your very last slide is to use a technique called iterative deepening.
Okay.
So you can start with like 20 warm-up iterations, 20 sampling iterations, and however many chains will fit on your machine, and then just keep doubling all those things until you hit your criteria. And you can actually see that because of that exponential growth, it's at most, depending on just how much you think you could shave by differing the number of warm-up and sampling iterations, at most going to be a factor of 3 off the optimal.
I love that. So I should say that the reason I like taking questions from Bob, even though we talk all the time, is I think it really benefits the audience to hear Bob's thoughts on this matter. And it's true that, so actually I did implement, you have some kind of schedule where what you'll do is you run a bit of warm-up, and then what you do is you generate one sample per chain that's like a proposal, and for that proposal you compute nested or hat, right, to see, have I met my convergence criterion? And if you haven't, then you keep going, and otherwise you stop. And so what you're describing is what would be a schedule for that that would ensure we don't stay too far away from the optimum. And that strategy, I haven't used a good schedule, but at least the strategy of checking repetitively, that works in terms of giving you these kinds of plots. Where it gets a little bit more tricky is picking a stopping rule that works well in high dimensions, that focuses on the dimensions that we care about, and also that doesn't introduce bias in Monte Carlo estimators. So even if empirically I haven't detected that bias, you can kind of make theoretical arguments that it should be here. So
yeah, but I think we know it's not going to be big.
We know it's not going to be big.
Right. So I think compared to all the other variants and bias, we probably don't need to worry about that so much.
So if we could have some guarantees that we don't need to worry about it, or some empirical evidence, then I would be very happy about that. But yeah, so this here, we can do it. This is coming. This is what's next. Okay, thank you. I think that's my time. So
let's thank our speaker again.